Weather forecasts are never 100% sure, but in recent years, the science of meteorology has been increasingly exact. In this program, we are going to give you a general idea of the basic principles of meteorology and of what creates the various climates on the planet. We will then look at the leading-edge technology meteorologists use today to make those famous predictions of theirs. The cows are lying in the pasture. It's going to rain. When I was little, my mother had a whole series of sayings like that. These sayings were passed down to her from her parents, who themselves had them passed down by their parents, and so on through generations. And just between you and me, my mother was often right. Human beings have always been both fascinated and awed by atmospheric phenomena. Often their lives depended on them. How many sailors left port, never to return because of an unexpected storm? In the old days, without accurate measuring devices and little scientific knowledge, man relied on his experience and sense of observation to draw conclusions, sometimes with surprising accuracy. Today, we no longer need the fury of the god Aelith to explain the winds, or Iris's glittering dress to describe rainbows. Meteorological phenomena, as complex as they are, comply with a set of physical laws, which are today fairly well understood. Whether a downpour causes floods or a snowstorm buries the countryside, the gods have nothing to do with it. Like everything else that characterizes our weather, such atmospheric phenomena come and go according to physical processes that, for the most part, are well known. It all begins with the sun. The sun heats up the earth and the atmosphere surrounding it. However, as the earth cannot heat up continually, it in turn radiates part of the energy received. Then it is the ground that heats up the atmosphere, which explains why air temperature decreases with altitude the first few kilometers above ground. Past 12 kilometers or so, the warming of the sun takes over. The atmosphere then very gradually heats with height. These exchanges of heat between the earth and the atmosphere are called vertical exchanges. Also, because the earth is a sphere and its axis is tilted in relation to its rotation around the sun, the polar regions receive less heat than the equatorial regions. The resulting differences in temperature entail horizontal heat exchanges to occur between the poles and the equator. The warm air from the equator moves toward the poles, and the cold polar air descends toward the equator. For the most part, since soil is a poor thermal conductor, these exchanges occur via the atmosphere and the oceans. It is to these vertical and horizontal heat exchanges that we owe the weather patterns we observe. However, the exchanges are much more complex than what we have just described. To start with, since the Earth isn't motionless but spins, air masses are deviated relative to the ground by a force known as Coriolis force. This deviating force applies to all bodies in motion on the globe. To understand how it works, all you have to do is walk around a children's carousel that is turning, like the Earth, counterclockwise. When you go from the periphery, where the rotational speed is high, to the center, where it is slow, you veer right. That deviation is due to the difference of speed between the periphery and the center. The same phenomenon occurs when an object moves from the equator to the poles. The air masses are thus always deviated toward the right in the northern hemisphere and toward the left in the southern hemisphere. This general movement of air masses is further perturbed by terrestrial relief and heat sources. All the air moving about above our heads has a certain weight, and the pressure it exerts is called atmospheric pressure. But atmospheric pressure is not always the same. It varies according to the air's humidity and temperature. So there are low-pressure areas called depressions and high-pressure areas which are called anticyclones. Wind is created by the differences of pressure between air masses. The wind has a tendency to blow from high-pressure areas toward low-pressure areas. However, it too is subject to the force of Coriolis and is deviated. So in a high-pressure area in the northern hemisphere, for instance, the wind blows from the center out to the periphery. Veered right, it blows clockwise. Again, in the northern hemisphere, but in a low-pressure area this time, the wind blows from the periphery toward the center. Veered right, it blows counterclockwise. In the northern hemisphere, an observer facing into the wind will always have the low pressures to his right and the high ones to his left. When a depression moves in, it is often associated with clouds and bad weather. In fact, ascending movements of air begin at the edges of the air masses that correspond to a depression. These ascending movements are located on the warm front preceding the depression, or on the cold front behind it. It is precisely such ascending air movements that cause clouds to form. As it rises, the temperature of the air decreases, and the vapor in it condenses into tiny water droplets. When there is a lot of condensation, the droplets enlarge and fall. It rains. When the temperature is below 0 degrees Celsius, the droplets become ice crystals, which by growing in size and assembling together, end up forming snowflakes. Once a depression has passed, usually good weather returns, unless local conditions bring about the formation of new clouds. In temperate regions, depressions can extend over several thousands of kilometers. On the other hand, in tropical regions, they are smaller and sometimes only extend over a few hundred kilometers. These little tropical depressions can reach considerable intensity, becoming cyclones, typhoons, or hurricanes. Fortunately, depressions like these are picked up by satellite, and warnings are issued. There are, of course, many other meteorological phenomena, like tornadoes, thunderstorms, and hail. What do they all have in common? They all tell us something about the kind of mood our atmosphere's in. Our atmosphere has its moods, but sometimes these moods turn into veritable tantrums. One of the most destructive forces of nature is the hurricane. We begin talking about a hurricane when winds reach speeds exceeding 117 kilometers an hour. Hurricanes develop in tropical regions during hot seasons when humidity is very high. They always head north, and in North America, they move along the eastern coastline, never along the western shoreline. We've discovered that certain chemicals released in the centers of hurricanes have the potential to make their clouds precipitate into ice. Perhaps one day we'll be able to slow hurricanes down by freezing them. Climatic conditions vary greatly around the world. Some regions are particularly vulnerable to hurricanes, others to prolonged periods of drought. The way climates are distributed around the planet is the result of a multitude of factors. Let's see what they are. We have long known about the great diversity of climates in our world. But why is this? The first factor, of course, is proximity to the sun. As a rule, the regions closest to the equator, where the sun's radiation is the strongest, enjoy a warmer climate than those located farther away from it. So climates vary according to latitude, that is the distance between a region and the equator. However, many other factors also influence climates, and they include the circulation of air masses in the atmosphere, proximity of oceans, or the geographical relief. We can, however, distinguish major climatic zones, and these are known as the equatorial, tropical, arid, temperate, cold, and polar climates. The equatorial climate is found in the regions bordering the equator, like Amazonia. Characterizing this climate are constant humid heat and heavy precipitations year-round. Real seasons do not exist. and the temperature never falls below 25 degrees Celsius. A little farther away from the equator, near the tropics, located in both hemispheres at 23 degrees latitude, you have tropical climates. Here again, there is no winter and the temperature very seldom falls below 18 degrees Celsius. Its only difference from the equatorial climate is the fact that it has a dry season and a rain season. The Caribbean and a large part of India, for instance, have tropical climates. In India, the rain season has a particular feature, the monsoon. It is caused by the arrival of hot air masses from the equator. The air masses are charged with humidity picked up over the Indian Ocean, and they bring substantial amounts of rain. The farther you move from the equator into tropical regions, the greater the dry season is, due to the presence of subtropical anticyclones, that is, high-pressure areas in which clouds cannot form. The climate becomes increasingly arid, and deserts, such as the Sahara, begin to appear. Beyond the latitude of 30 degrees or so, a major change occurs. You begin to see actual thermal seasons: winter, spring, summer, and fall. Indeed, beyond that latitude, the inclination of the Earth's axis is such that a region's distance from the sun, hence from its heat, varies considerably during the course of a year. The seasons observed are, of course, reversed in the southern hemisphere. The regions located between 30 and 60 degrees latitude are often associated with a temperate or moderate climate. However, there are slight differences. These areas of the globe are, due to atmospheric flow, subject to westerly winds. Therefore, regions like California or Europe, located on the west coasts of continents, are being constantly swept by air masses from the ocean. Their climate is oceanic. It is characterized by constant humidity and moderate temperature changes from one season to the next. The ocean acts as a moderator, since it cools in winter and warms in summer more slowly than the continent. Often the coldest month will record a mean temperature that is superior to 3 degrees Celsius, and the hottest, a mean temperature inferior to 22 degrees Celsius. On the other hand, regions located farther east on the continent are not affected by the oceans. Here we have cold continental climates. Their common points are a very cold and dry winter and a hot, humid, and rainy summer. Beyond the latitude of 60 degrees reigns the polar climate. In summer, the thermometer rarely exceeds 10 degrees Celsius, and in winter it can plummet to minus 80 degrees Celsius. The ground is permanently frozen. The list of climates we have just given you does not, however, take local characteristics into account. A number of factors, like the presence of cities or a particular geographical terrain, can create local climatic conditions we call microclimates. Since it was formed, Earth has experienced all sorts of climates, including ice ages. But it's the relative climatic stability during the past 10,000 years that has enabled our civilization to develop. Even though man has shown amazing adaptability to inhospitable climates, he will never be completely independent of climatic conditions. Today's meteorologists count on supercomputers to process data generated by thousands of weather stations throughout the world and by numerous satellites that scrutinize the planet on a permanent basis. The atmosphere surrounding the globe is in perpetual motion, and this means that our weather may well depend on the weather occurring thousands of kilometers away. The meteorologist's job is to predict the weather, hours and even several days in advance, and is therefore quite complex. They require access to very powerful computers and to numerical weather prediction. Numerical weather prediction calculates the future state of the atmosphere based on its current state by using mathematical models that describe the changes as they happen. The models describe, for example, air mass movement, precipitations, and wind or temperature variations. To describe the state of the atmosphere, it is cut up into boxes, the dimensions of which vary according to region. Horizontally, they can measure from a few dozen to several hundred kilometers, and vertically, from a few hundred to several thousand meters. The smaller the box, the more accurate the forecast. The atmosphere is thus cut into some 20 levels up to an altitude of 30 kilometers. Beyond that, the influence exerted by atmospheric conditions on the weather is deemed negligible. Initial atmospheric state is described by the mean values of pressure, temperature, humidity, and speed and direction of wind flow in each box. The amount of data necessary is therefore substantial, especially for long-range forecasting. Consider that an air mass located over Japan can take 5 days to reach Canada. This means that a 5-day forecast has to take into account atmospheric conditions around the world. The items of data processed simultaneously can be more than 1.5 million. This is global forecasting. All this information on the atmosphere comes from various sources. First, there are nearly 14,000 ground weather stations around the world, 9,000 on land, and 5,000 on ships or installed on buoys. Every 3 hours, these stations measure the air temperature, pressure, humidity, and speed and direction of wind flow. To obtain similar data, but in altitude, meteorologists use radiosondes. A radiosonde is an instrument carried aloft by a hydrogen-filled balloon. After transmitting by radio all the data gathered during its climb, it explodes at an altitude between 25 and 30 kilometers. There are about 700 radiosonde stations around the world. Each one launches 2 radiosondes every day at midnight and noon exactly Greenwich time. Other data is gathered by polar orbiting or geostationary satellites, which have the advantage of encompassing a large portion of the globe. In meteorology, international cooperation is essential, and all the data gathered around the world is automatically forwarded to 3 centers, located in Melbourne, Australia, Moscow in the Soviet Union, and Washington, D.C. in the United States. The data is then retransmitted to national forecasting centers for compilation, selection, and processing. The processing of the data, that is the calculation of the atmosphere's evolution in time, is carried out by supercomputers capable of performing 400 million operations per second. The results are represented on maps that describe the state of the atmosphere 12 hours, 24 hours, 36 hours, and more after the initial time the data was collected. Today, you can follow the movement of the atmosphere in animation on a graphic screen. You can, for instance, observe the movements forecast for certain precipitation zones. Numerical forecast results must, however, be analyzed and corrected by meteorologists on the local level, based on more detailed observations. These can come, among others, from weather radars, which enable meteorologists to pinpoint areas of precipitation within a 300-kilometer radius and determine the height of clouds and probable magnitude of the precipitation. The main problem in weather forecasting is accuracy. Indeed, the rough atmospheric pattern now in use makes it impossible to forecast local weather occurrences such as tornadoes, which are only manifest over a few square kilometers. Weather forecasting is done on a major scale, and this accounts for user disappointment when the weather is not what the weatherman predicted. In any event, weather forecasting is a science that is progressing rapidly. Today's top weather service is the one in Reading, England. Their 3-day weather forecast is as accurate as the 2 or 2.5-day forecasts made by other weather centers around the world. On TV earlier, they predicted a beautiful evening. But when the horses yawn, or the dog eats grass, when the bees stay real close to their hive, it means it's going to rain. You never know.